everyone, and welcome to another Astronomy on Tap. I hope you all are doing well, and I hope many of you got to see Perseverance land on Mars. I know I was excited because it was really cool just to see the live footage from Mars, and where we got to see a video of us landing on another planet, which I thought was amazing. So tonight we have two amazing guest speakers. So be sure to grab your favorite snack or drink. My personal choice is peppermint tea, and so we can drink it all into the universe while we listen to these amazing topics. So our first guest speaker up tonight is Dr. Stephanie Jarmack. She obtained her PhD in planetary science from the University of Central Florida, and she basically was investigating regolith in microgravity conditions. And she's now here in San Antonio with Southwest Research Institute, and she's doing a bunch of different studies like of Saturn's rings, metallic asteroids, and mitigation strategies for dust on different missions. So, Dr. Jarmack, are you there?
All right, hello, can you all hear me and see me?
Yes, we can.
Awesome, perfect.
The floor is yours. Tell us awesome things.
I will do my best. All right, so I'm going to go ahead and attempt to share my screen. Here we go. All right, hopefully everybody can see my title slide there. So yeah, thank you so much for having me and inviting me to give a talk for our Astronomy on Tap. It's been quite a week for some of us who are local here in the San Antonio area. So one of my drinks of choice is water, because we didn't have access to this for about a week, and some of us still don't really have access to water. So that's great. Also have an old fashioned, because it's Astronomy on Tap. You have to have an adult beverage, I think. So yeah, I'll go ahead and get started with my talk. So space dirt in 0 and low, I have to sort of caveat that, gravity. So a little bit of background on me. I'm a postdoc here now at Southwest Research Institute. I obtained my PhD from University of Central Florida back in April, where I defended my PhD over Zoom because you're still in a pandemic. And then I arrived here in October, and I'm very fortunate to be working with Dr. Tracy Becker, who will be speaking after me. But what I'm going to talk about now is what I had focused more on during my PhD at UCF. And so that was investigating this space dirt in different gravity environments. So let's see. An overview of my talk. So I'm going to talk about what I mean by space dirt, and why we are interested in studying it in these different gravity environments, and how scientists can achieve these lower gravity environments on the Earth and beyond, of course. And then throughout, I will be talking about various space dirt experiments in my presentation. So what do I mean by space dirt? So the more scientific technical term for this space dirt is regolith. And so that's defined really as the unconsolidated rocky material that covers the surfaces of various planetary objects. And that doesn't really mean just as how we know it, dirt. It could range from 20-meter sized boulders down to sub-micron sized dust grains. But I have some zoomed in pictures here of what these grains might look like. So in the top picture here, we have port sand. So it's like sand you might see at the beach or playgrounds. And those grains are more sort of rounded. And those shapes are structured through processes that we know in the Earth that are through erosive processes that we don't really see on different airless bodies such as asteroids or the moon, where the more jagged shapes of these grains are due to things like micrometeorite bombardment and other processes that we don't observe on the Earth. And so these grains, this regolith, this space dirt, right, is fundamentally different mechanically than the dirt that we know and love on the Earth. And so observing it in and of itself and simulating it, as some corporations do, like Exolith Labs at UCF, allows researchers to better understand how the space dirt sort of responds to our inputs. So we can do amazing things like land on Mars, as Perseverance did, and I hope that many of you tuned in to see that landing. And I have this picture here as well of Itokawa, an asteroid that's covered in different sort of populations of grain sizes of this regolith material. So I mentioned what space dirt is. So why are we interested in studying it in this low or zero G environment? So there are certain forces involved between the grains that are sort of masked by this higher gravitational acceleration that we experience on the Earth. And the stickiness, the cohesive interactions between the grains, or the electrostatic response of the grains is quite important on these smaller bodies, smaller airless bodies. And so one of those components is triboelectric charging. And so if you were to Google triboelectric charging and click on the Wikipedia page, what they found was most important to demonstrate this is to show a cat that's covered in these packing peanuts. So the static electricity of these grains essentially is much more important on places like the moon and other airless bodies. And when I talk about low G, I mean more like partial fractions of the Earth's gravitational acceleration. So these are still quite large bodies, but they're smaller than the Earth. So on the moon, it's about a sixth of the Earth's gravitational acceleration. So there are still some forces that become much more prominent than what we experience on the Earth. And on Mars, it's about the third. For asteroids, these are much smaller bodies, so they have even smaller gravitational accelerations and fields that are more inhomogeneous as well. And so, I provide the range here, but then we talk about zero G, what we really mean is this term called microgravity. So you're not really in a zero G environment, say when you're on the International Space Station. You're actually in this free fall environment where the forces acting on you cancel out so that you are experiencing this weightlessness and this zero acceleration. And so this regime is really, you're looking at space dirt in zero gravity or microgravity. This is particularly relevant for studying the earliest stages of planet formation, where we have really no forces acting on these particles and are just looking at the very first pieces of dust that come together to form planets. So that comes into why study the space dirt in this low gravity environment. So as I said, planet formation is one of the key components. So understanding the vast diversity of planets in our solar system and beyond, to understand how they come to be really requires us to know the fundamental beginnings of this planet formation, which starts from these submicron grains and how they coagulate together and how they come together at these very low speeds, which requires a microgravity environment to study experimentally. So I just show this little video here, these dust aggregates coming together and sticking together. So we can actually perform these experiments with these like dust clumps coming together in a microgravity environment, which will then provide experimental inputs to planet formation models. And I hope many of you were able to see this amazing video that NASA posted of Perseverance landing on the surface of Mars. So one of the other benefits of studying the space dirt or dust in the relevant environment is we want to be able to design these landers or these spacecraft to go and study the surfaces of these different bodies that have this material coating their surfaces that are completely different from what we experience on Earth. So to do so requires a lot of experimental inputs and modeling to really understand how it's going to impact, and see they succeeded there, how it's going to impact your spacecraft instruments and things of that nature. And I show this little figure here of the different companies that have been funded by NASA to develop the next human lander system, or propose to do so, to land on the moon. And so there are certain dust mitigation strategies that need to be implemented to best design those spacecraft. And then lastly, there are many reasons I want to study space dirt, but another reason is not just to land on the surface, but to even interact with directly and sample and take, and then utilize for human exploration reasons. So this video clip that I show here is OSIRIS-REx doing their touch and go sampling of the asteroid Bennu. And for them to design the spacecraft and understand what's going on there, they really needed these experiments to know what was going to happen when they had this, very slow like air push in this very low gravity environment interacting with the regolith. And so, yeah, they were successful there too. But we can always benefit from more experimental inputs. So this next slide shows a few different experiment platforms that we have available to us as scientists to perform these microgravity experiments. And so in order from left to right in these figures here, basically shows longest duration microgravity environment to shortest. So this image here is a CubeSat, and it's a CubeSat that I worked on as a major part of my dissertation called CubeSat. And so on orbit facilities like satellites, CubeSats, the ISS provide the longest duration of microgravity environment. So you can really see how these particles evolve over time. And then I have an image here of Blue Origin suborbital rocket, where you can achieve a few minutes of microgravity time, which is amazing for studying these interaction effects. And then here, the zero-G plane, or better known as the vomit comet, maybe, where you have parabolic flights that allow researchers to be weightless for 30-ish seconds and try to perform their experiments in that brief amount of time. And then here is our 12-foot drop tower at the University of Central Florida Microgravity Research Center. And in this environment, you basically walk up the top of the stairs and drop your payload. And when that payload is in free fall, that's a microgravity environment, but you only get 0.7 seconds to perform your experiment. So another option for a drop tower is the Bremen drop tower, which, as far as I know, I believe is currently providing the longest amount of microgravity duration for a drop tower because of its catapult mechanism. So if you were to just drop an experiment from a height of 480 feet, you get around 4 seconds or so, 4.5 seconds or so of free fall time to perform your experiment. But they have this unique setup where they launch their experiment up and then it goes into free fall. So it sort of performs the same effect of the parabola part of a parabolic flight, where then you double the amount of free fall time that you have. So I'll show you what that looks like here in this video clip. So they launch the experiment up, and it's still in a microgravity free fall environment while they are recording their data. And it falls back down, and it lands safely to be collected by the researcher. And I'll show you what my experiment looks like here, and hopefully you can hear the sound there. But I'm carrying one of my dissertation experiments up to the top of the drop tower, and I am
all right, you ready? No, it's just I'm gonna aim for like the center of it, but it might bounce towards you, so if you could try to catch it, but
yeah,
do your
they
best.
could try to catch it, right?
3, 2, 1, drop.
So this is one of my experiments that is part of my dissertation. And so we have our 12-foot drop tower, and I was lucky enough to have a very light experiment, so I could just drop mine. And since it was so light, it had the hazard of bouncing, but luckily it pretty much always stayed contained in the styrofoam barrier that we would set up. But I can just show you a couple examples of what some of my experiments look like. So what I was looking at is how the cohesive interactions of the grains changes in a microgravity environment. So I'll just move to a clip here. You can see some of that granular material sticking to the surface of the projectile as it's lifted up in a zero-G environment, and those grains wouldn't stay adhered to a projectile if you were to do the same sort of thing in a 1G environment. So we were studying how grains stick together essentially in microgravity. So we could still do a lot of interesting science with just our 12-foot drop tower. And here are a couple other examples as well. This is from the Bremen drop tower, where they're looking at triboelectric charging effects of grains. And then here is an example of now one of my coworkers at SWRI, who was then a student of my advisor in my PhD program, using that 12-foot drop tower where we would collide these dust aggregates together, which is relevant to early planet formation. So for parabolic airplane flights, as I had mentioned before, you have this, you're going up in a regular airplane pretty much, but then you go 45 degrees, and in that ascent, all the researchers are laying down on the floor, and they're being pushed down by 2 Gs of force. And then during that turnover portion, then everybody is in free fall, floating around, and you have about 30 seconds to perform your experiment before you have to get back down on the floor, and you're pushed down with another 2 G, like a very intense roller coaster. So I have this little video here showing our success after we were finished with the experiment. We're just floating around. Here's our experimental storage unit. And some people are still very sick because they don't call it the vomit comet for nothing. But as you can see from that, it is quite a brief amount of time to try to set up an experiment. But we were quite successful with that. So here's an example of one of our experiments where we're shooting a projectile into that regolith material. And we're looking at how much of those grains adhere to the surface of the projectile, as well as how much dust is lofted off during that impact. And here's another one where we were quite excited. We were really psyched for mass transfer. So that was very exciting for us. And another option for a microgravity environment, as I mentioned before, was a suborbital rocket launch. So this is Virgin Galactic Spaceship 2 inaugural flight to space, or what they defined as the boundary of space. It's the Kármán line. So you can see White Knight taking up Spaceship 2, and once it reaches a high enough altitude, then it releases the space plane, and then the space plane like goes right up into space, carrying along with it private astronauts, as well as now these private organizations are allowing researchers to perform these microgravity experiments on board their space plane. So it's pretty exciting. And then here's a picture of me and one of my lab mates working on that payload a little before integrating it onto Spaceship 2. And then I'm lucky enough to be quite short, so I was able to stand right in front of Richard Branson post-flight. So it was pretty exciting for me. And here is an example of one of our experiments on board a suborbital flight. And this happens to be on a Blue Origin rocket. But what's interesting to note is as this projectile launches into the regolith material, it picks up a significant portion of that regolith and leaves off with it. And we don't see that in a 1G environment. So it really requires this very microgravity environment to see this effect. But it's worth noting that for the same sort of energy impact conditions, depending on the regolith characteristics, you will see a quite different effect. So in the previous video that I showed, it was quartz sand. And in this video here, it's Martian regolith simulant. And we have the same impact parameters, but the result is this blanket of ejecta that's produced. So we learn a lot of interesting things about how dust responds to these various input energies by performing these experiments. And so the last microgravity platform I'll talk about is our CubeSat. Back in January was the inaugural flight of Launcher 1, so Virgin Galactic's Boeing 747 plane that had one of its wings fortified to hold a rocket. And it's basically like a traveling launch pad. And once it reaches the appropriate altitude, it drops the rocket, and the rocket will go up into space. And in this case, it launched about 10 CubeSats into low Earth orbit, including QPACE. And so QPACE is our 3U CubeSat, and I show this little simulation here that I created to demonstrate what we hope to see inside of this CubeSat. And so what we're looking at is the earliest stages of planet formation, looking at the low velocity coagulation of these different sizes of particles. We have some dust in there, some millimeter size chondrules in there as well, and centimeter-sized quartz particles. And we have a GoPro looking down, or actually now it's a Raspberry Pi cam, but looking down to record all of these collisions and hope that this will provide valuable inputs for planet formation models. So the takeaways from my talk are studying the space dirt in different gravity environments helps us learn more about the earliest stages of planet formation and how these particles coagulate together. Inform decisions for how spacecraft interact with planetary surfaces, and to better understand how for in situ resource utilization and better understand remote sensing observations of the surface of these bodies, the various platforms that are available to study the space dirt, regolith, and microgravity environments, including drop towers, parabolic flights, suborbital rockets, and on-orbit facilities. And there are lots of exciting recent and upcoming missions that benefit from better understanding this regolith and a microgravity environment. So I put up all of the pictures from the Wikipedia page for regolith here, and I'll take any questions.
Thank you again, Dr. Jarmak, for the amazing talk. It's really cool to see all these different experiments that you're able to perform. And I never knew some of these different things of how regolith is able to stick to certain different types of things. So a really fascinating topic. So folks, if you have any questions, leave it in the question and answer section and we'll be happy to answer them. All right, first question off the top. Does the study of space dirt and microgravity also help us study the formation of gas giant planets, or does it strictly apply to rocky planets?
Great question. So it does in the sense that we believe potentially that the formation of gas giant planets could start as this formation of this terrestrial core, that then if it's in the right environment, we'll have this sort of rapid growth of gases around it. But in order to form that sort of terrestrial core, like once you reach around 10 Earth masses or so, it still requires the same sort of initial conditions of these smaller particles coagulating together, if that makes sense.
Question number 2, after all this interesting research, what comes next for you? And what questions do you still have that you'd like to gear your work towards?
Yeah, no, that's great. So what I'm really excited about is to hopefully see some of these results from our CubeSat, because I'd really love to work on developing like a statistical model based on the interactions between the particles that we see there. But I'm really interested in sort of branching out and hopefully developing someday a mission of my own to go really like get more samples, because I think we need to get more samples of this space dirt to study it here on Earth.
All right, any other questions? All right, if there are no more questions, thank you again for a wonderful talk. And oh wait, when I'm getting one more. Hang on.
All right.
Sorry. Here we go. Towards the gas giants, is there an experimentation with the observation of gases in low gravity?
So yeah, I'm not really familiar with anything that would benefit understanding gas giant formation, in the sense that you would need such a wider scale, like the experimental inputs for that, the gas giant formation for the gases involved, it really benefits more from numerical simulation than anything that we could really do, as far as I know. But the earliest, because the reason that we do the earliest stage, honestly, is because that's what we have access to. Like you would need to start from like the core, so you'd have to have 10 Earth masses and then have this access to all of these gases, right? So really the reason why we're interested in performing experiments of the earliest stages is because those are the particle sizes that we can actually work with in our size restrictions.
All right, next question. What are some potential applications for your findings with respect to mitigation strategies for entering surface habitats and not tracking dust in?
Yeah, right. So I'm actually working right now on trying to figure out ways to mitigate dust and for the human lander system. And there are certain, I mean, I'm not particularly working on materials that would allow for this mitigation strategy, but I know NASA has selected several different teams, including one from UCF, to develop these technologies to basically repel the dust away. And what I'm currently working on is trying to quantify the amount of dust that we'd expect from a lander to like be lofted and then accumulate. And then from then on, we have to figure out like, okay, how do we keep it from interacting with our instruments? But I'm not a material scientist, so that's more for me to give to the material scientists to let them figure out.
All right, next question. How do you get the data from the CubeSats?
That's a great question. Yeah, so it's really the same way that you get data from any spacecraft. So we have a ground station that's being developed at the University of Central Florida, and there's an antenna on the CubeSat that'll be relaying the information from our satellite. So we have actually the computer on board our satellite is just a Raspberry Pi. And I worked significantly on the data compression system to make sure that it wouldn't take too long for us to communicate this information back down. But yeah, it's just an antenna relay down to a ground station, and hopefully we'll be able to hear from it soon. But since it is video data, it will take a bit of time for it to downlink to the ground station. So over the course of a full experiment, it might take around 2 weeks to get that amount of data.
All right, are there any other questions? One quick question. Does regolith on other bodies pick up a static charge like they do on our moon?
Yeah, no, it's a great question. So the reason that we get that static charge on the moon is because of the way that sunlight and energetic particles interact with that regolith. So absolutely, we see this radiation effect producing these charged particles. I'm not quite sure it's to the extent of this sort of like lunar haze that we observe potentially, but that does definitely happen where we have radiation effects charging regolith grains and other bodies.
Okay, next question. If you could get a sample from anywhere, where would it be?
Oh man, that's a great question. I mean, right now, what I'm most interested in, because I just submitted this proposal, is for the asteroid Psyche, because we're really interested in this potentially metallic asteroid. So if we could, if I could get a sample from Psyche, I'd be like a trillionaire, right? But yeah, it's hard to say in terms of like the scientific value that we'd gain. What would be the best sample return? But I'm all about this upcoming mission to Psyche.
Are you next question? Are you using the RPI transmit, or does the RPI communicate with dedicated RF hardware?
I will be honest, and I'm not sure how to really answer that question. So I assume they're talking about how our satellite communicates to the ground station, and unfortunately, I don't know enough of the jargon to, or worked enough with the communications people to be able to answer that.
All right, are there any other questions? All right, if there are no more questions, thank you again for indulging us on this wonderful topic.
All right, thank you for having me. Really appreciate it.
All right, so next up we have Dr. Tracy Becker. She is a planetary scientist at Southwest Research Institute, and she studies a bunch of things like rings, moons, asteroids, the Cassini spacecraft. She's a part of the Europa Clipper mission. She's worked with Hubble. She's worked with the Arecibo Observatory and much, much more. She is a woman that wears many hats. And she's one of the coordinators for Astronomy on Tap. So today she decided to talk about the legacy and future of Arecibo. I know it broke my heart when I saw the video of the amazing observatory falling apart, and it broke my heart because I always wanted to go see there. So tell us what the future of the Arecibo Observatory holds.
Thanks, Michelle. Can you hear me?
Yes, ma'am.
All right.
The floor is yours.
As I share my screen real quick, and I'll put this into slideshow mode. Can you see my slides?
Yes, ma'am.
All right. Well, thank you for that awesome introduction. I think it means I've done this too many times with you guys now that you know you can name all those different things. It's pretty good. And yeah, thanks everyone. Thanks Stephanie. That was an awesome talk. And thanks for joining us for this virtual Astronomy on Tap. I will at first just let you all know that this was originally, of course, an event that happened in person, and Astronomy on Tap is worldwide. It's definitely across the nation, and a lot of the different entities are now doing them virtually. So I recommend following Astronomy on Tap generally, their website, and you can see other talks that are going on. The team you can see here, the Astronomy on Tap team, most of us there. But a super huge thanks to Scobie, to Michelle, to the team that's been hosting this virtually. They've been really doing an awesome job, and we're kind of just helping find speakers. So it's really awesome to partner with such a great institute here in San Antonio that's doing such a great job with outreach and education too. So thanks Scobie. Okay, and so we'll jump into my talk here. For those of you who have known or followed Astronomy on Tap for a while, you probably know that this is one of my most favorite topics, and I'm going to try not to talk for like 2 hours on it. But yeah, so this is a talk that's going to talk a lot about the legacy of Arecibo. So I want to talk a lot about why it was such a unique facility, what was the really cool science it was doing, and what's in store. What are we doing now, and what might be the future for the Arecibo Observatory? The Arecibo Observatory is built into the karst topography of the island of Puerto Rico. So you actually have this natural formation that's kind of perfect to build a giant spherical dish. Now this is a radio telescope, so it's not a telescope with mirrors the way you think of it. This is because the wavelength of the radio waves are so long, you don't need a perfectly nice mirror. What you can actually have is this mesh material, which is what you see down on the ground there. This was finished being built in 1963. It was originally actually built for the Department of Defense to detect missiles in our ionosphere. So it was really meant to study parts of our upper atmosphere to understand what the ionosphere's response might be to incoming missiles. So it actually had a very different original purpose. But once they were building it, they were like, hey, we could do a lot of really cool science work with it. So of course, they not only, a few years later, it really got transferred to be completely a scientific facility for the most part. And we started doing astronomy, ionospheric studies, and planetary science, which I'll talk about all three of those. The telescope dish is 305 meters across, or 1,000 feet across. It was the largest telescope from when it was built until China's FAST telescope in 2016. And just so you guys understand just how big this is, I mean, you can see some normal buildings in the bottom screen there, but let me click. That's 3 American football fields across. So it is huge. And this platform that you see hanging above it is 900 tons and hung over 350 feet above the dish. So this was a pretty insane architecture engineering feat to begin with. And it operated and really did some incredible stuff for a really long time. And so this is really high up. I have the pictures to prove it. So that's me on my way up to the top in this kind of really scary rickety cart thing that you can take up there. Or you can also walk up on the catwalk, which I think you can kind of see in this picture, the long like connection thing at the bottom from the platform down to the ground. You can actually walk that way too. But it's high up. It's a beautiful view. But it's that's actually where a lot of the instrumentation is up inside that platform. And I'll talk a little bit about how that all works as well in a minute. So you might be thinking to yourself, this place looks familiar. So you maybe know this observatory from the movie Contact or the movie Goldeneye, where they kill Sean Bean again by throwing him to the ground of the dish. Or if you don't, you might just be a young person. So maybe that's why you don't recognize it from these movies. And before I really talk about the science, I just want to give a quick understanding of why I often talk about Arecibo and what my connection with the facility is. So my career was actually started at the Arecibo Observatory in 2008. I did my first internship there, worked on some asteroid science, and obviously fell in love. If any of you have ever been to Puerto Rico or visited or were lucky enough to visit the observatory, you know, you're in the middle of this jungle. You can, at night, you hear the coqui frogs, you hear, you know, you get these big, awesome thunderstorms throughout the day. And then you're working at your office and you look out your window and there's just this incredible engineering feat in front of your face every time you look up. And it's truly inspirational, and it was breathtaking every time. So I got to go back and do a little bit more research in 2009 and 2012. And then I hadn't really been there in a while. But when the University of Central Florida became the management entity of the observatory, I got back involved because in case you didn't know, there's a UCF theme today where I also was a graduate student at the University of Central Florida, as was Stephanie. And so I actually ended up becoming a science communication lead and also working with the team that does radar observations using the facility. So science communication lead, at the end, I'll have a link where you can see some of the newsletters that we created that I kind of helped or led us putting together every quarter. Okay, so enough about me. We'll talk a little bit more about the science. So there were 3 entities of science that I'm going to talk a little bit about. The first is the space and atmospheric science. You can see the ionosphere. This was, you know, the original purpose, right? Was to study this atmosphere component of things. You can kind of see what the ionosphere is. It defines, you know, the exosphere, the thermosphere, the mesosphere. Parts of the upper atmosphere really comprise the ionosphere. And what Arecibo could do was it could look at space weather. So this is the interaction between, you know, particles coming from the sun and how it's interacting with our Earth's atmosphere. We could understand extreme weather conditions by continually studying the ionosphere. There's a lot of other kind of cool concepts on this slide you can see. We were actually able to do different techniques, including incoherent scatter radar. So this is an active observation where we shoot a radio signal into the atmosphere and see how it gets reflected back. We also did other cool things called like these heating campaigns where we actually heated up the ionosphere above the observatory and then watched how it created like cavities in the plasma of our ionosphere and watched how the atmosphere reacted to that heating. So there was a lot of really cool stuff being done at Arecibo that's not really done anywhere else. There's different versions of this in different places, but remember, this was the biggest dish in the world and also had these facilities and capabilities. So it was a really unique facility to do these things. Since it's astronomy, I'm also going to give a little shout out. One of the coolest things that I thought when I realized we did at Arecibo was that when asteroids come into the atmosphere and burn up as meteors, and you see them as shooting stars, they vaporize, but like it doesn't mean it goes into the ether, right? It doesn't just disappear. Actually, material from those pieces of asteroids get deposited in our atmosphere. And one of the things radar is good at is detecting metals. So you can actually end up seeing the deposited metals from these evaporated meteors as they kind of dissipated into our atmosphere. So I just thought that's such a cool aspect of what was done at the Arecibo Observatory. So it also, you know, really focused on studying long-term changes in the atmosphere, making really unique double type of measurements with all of these different capabilities that it had, was really what made it stand out in the space and atmospheric science side. it really starts to pop, I think, in the radio astronomy side. So we had just the ability to do a lot of really, really, really cool stuff in the universe. So we're talking pulsars, which are these highly magnetized dead stars that are giving off energy. I'll talk a little bit about that on the next slide, actually. You can study the effects of black holes. You could study star-forming regions, these fast radio bursts, which are these things that we don't even really know what causes them, but they're this intense amount of energy that we're able to just spot. The first exoplanets were discovered with Arecibo in the 90s. We can do spectral analysis, so studying the composition of different objects in the universe, understanding that there's a large scale structure to the universe. And also, we can actually combine the Arecibo Observatory with other radio telescopes across the globe in this technique called the very large baseline interferometry is the technique. And you can do not usually all of the telescopes, but some subset of all of these different telescopes, and you can get that much bigger of a baseline for a telescope. And that's how they saw the, for example, that image of the black hole that came out a couple years ago. Even though Arecibo wasn't in that one, that's the same technique that Arecibo does participate in, or did. Some of the main highlights was that it, the biggest one right off the bat in 1974, the Arecibo Observatory discovered the first binary pulsar. So again, these pulsars are these magnetized dead stars that end up having these jets of energy emitted from the poles. And this led to a Nobel Prize in physics. In 82, it discovered the first millisecond pulsar. So that's one of these dead stars that's maybe the size of, it's bigger than the Earth, spinning on its axis once every millisecond. Could be about the size of the Earth. It's big to be spinning once every millisecond. The first ever exoplanets were discovered, ingredients for life in a different part of the in a different galaxy, the distances to things like the Pleiades, the first repeating fast radio burst. So that's that weird energetic thing that we were talking about. And one of the really cool things Arecibo was doing right up until the end was part of this nanograv project, where it was looking at how gravitational waves were affecting pulsars. So Arecibo has such a good sensitivity and timing for these pulsars that it could tell if a gravitational wave had affected them. So we were actually a different way to study gravitational waves, which I think is awesome. And you might be familiar with some of the cool stuff it's done in the SETI world, so the search for extraterrestrial life. The Arecibo Message was sent in 1974 by Frank Drake with help from Carl Sagan. You might recognize those names. And this was really a message to be sent out to the universe. And hopefully if an intelligent species came across that message, they'd be able to decode it and know a little bit about humans on Earth. In 2019, students competed to design a new AO message for the 45th anniversary, and it was going to be transmitted, I think this year, or maybe even at the end of last year, but unfortunately that wasn't able to happen. Okay, so if I haven't seemed excited yet, we're going to get into my topic, which is planetary science. So one of the major components of the Arecibo Observatory was the planetary science aspect. And the way we really did this was with radar. So this was an active observing technique where you would actively send a signal out from that dome of the platform. You'd send it down into the dish would bounce it back into space, and we would see an asteroid. This one might look familiar, it was in Stephanie's talk. You could see an asteroid, you could see a planet, you could see whatever you were trying to look at. And then you would see the signal that gets reflected off of that object, and you would be able to learn a ton about it. And when I say a ton, I mean super accurate, awesome information about them. So the precision that you get with this technique is incredible. So you can actually determine these objects that are, tens of millions of miles away, hundreds of millions of miles away in some cases, to extremely precise distances down to tens of feet. And then their velocity as well. So if they're coming toward you or away from you, and if they're spinning, down to inches per second. So you're really, really getting super accurate, precise information about these objects. And it works similar to some things that we have on Earth. So a radar gun that a police officer would use to track the speed of your car is very, very similar to what we're talking about here. And bats use sonar with sound, so it's a little bit different. It's not light waves, it's sound waves. but it's that same concept that they can kind of figure out what's in front of them or what's around them by seeing how that echo signal, the signal gets echoed and reflected back to them. So what did we look at with this cool radar technique? We looked at a lot of planets in our solar system. In 1965, radar showed that Mercury rotated every 59 days. So we used to think it was tidally locked with the sun. So we thought that it orbited in 88 days. We knew that, but we also thought it would spin in 88 days, like our moon does around the Earth. But it turns out, using Arecibo, we found out that was not the case. It actually rotates faster than that. So you actually get sort of a period, a day and a half-ish per year. In 1972, I mean, Mercury, Arecibo just was all over Mercury. In 72, it detected measurements in the change in Mercury's orbit that basically confirmed predictions made by Einstein's theory of general relativity. So really cool stuff. In 92, it detected these, you can see this image here of Mercury, where we saw this really highly reflective aspect of it in these craters near the poles of Mercury that were suspected to be ice and were later confirmed to probably be ice once we got there with spacecrafts. We looked at Venus. So the radar can actually, I didn't mention on the last slide, but I had it written. The radar can pierce through clouds, the wavelengths we were using with Arecibo. So you can go rain or shine, day or night, doesn't matter. You can observe with radar, with radio, but also with radar. So we could pierce through the clouds of Venus. This is pretty unique because most telescopes can't see below the cloud deck. Same with Saturn's moon Titan. We also have a cool image of Saturn's rings from radar. So there's a lot of really cool just astronomy, planetary science, solar system science that we were doing. But the biggest thing I would say Arecibo was doing at the time, up until last year, was planetary defense. So these are all the asteroids that we know of in the near Earth space. So you can see these different orbits here, and you can see where the Earth is. And so you can see there's a lot of objects floating around in space. Now, keep in mind, these dots on this scale are way bigger than most of the asteroids. So it looks a little scarier than it really is. But it's important to know where all these things are. And you might ask yourself why, but you might already know the answer, which is we would prefer not to go the way of the dinosaur. So if there is an object coming towards the Earth, we'd like to know about it. We'd like to be able to have some advanced warning and have a plan to mitigate it. And so there's actually a department in NASA called the Planetary Defense Coordination Office. And so this coordination office actually works to track all asteroids that are larger than 140 meters and come within about 20 times the distance of the moon. So the moon is pretty far away. So this is pretty far. But the point is that if they're coming that close and they're that big, we want to know where they are and where their orbits might take them in the future. And again, Arecibo's precision of knowing exactly where they are and how fast they're going, you can actually trace out their orbit into the future for decades, if not centuries. And so Arecibo doesn't detect the asteroids. That has to be done with more traditional methods with telescopes, with other kinds of telescopes. But if one comes close enough for Arecibo radar, which was the most powerful radar system in the world, we could bounce that signal off and we would know a little bit about it. Now, just for all of you that are here tuning in from San Antonio, 500 feet is, just a little bit smaller than the Tower of Americas. So basically, we're looking at for all asteroids that could kind of just, if you were to stand on the top of the asteroid, maybe you could wave to people having dinner at the Tower of Americas. And so these are big asteroids, but they're not, they're small in terms of space, and we're still being able to find them with these kinds of techniques, which is pretty cool. The most important research ever done at the Arecibo Observatory was the study of a triple near-Earth asteroid. It was the first time this asteroid was an asteroid was determined to have 2 moons. We had seen asteroids with 1 moon before, but we had never seen a near-Earth asteroid with 2 moons before. And we modeled it. We used radar data plus data from other telescopes to understand what the shapes of those asteroids and the asteroid and its 2 moons looked like. And so I'll admit that this probably isn't what most people would consider the most important work that Arecibo did. This was just my project with Arecibo. But that said, it is actually a very cool discovery and does usually make their discovery list of being the first triple near-Earth asteroid. Since then, Arecibo found, I think, 2 other triple systems. So they're not very common, but there are a few of them, and I'm pretty sure they were all detected at Arecibo. The other thing Arecibo was doing a lot of was mission support. So Stephanie's talk had a lot of really cool stuff about, the surface and how this regolith stays on the surface of these airless bodies, and what happens when things collide into them. So NASA recently sent a mission called OSIRIS-REx to the asteroid Bennu to collect a sample. And you can actually see the radar data on the bottom left, and then the model in the bottom center, and then the actual what it looked like when we got there. So you can see they're all pretty similar. Okay, and now I realize I'm talking too long. So Lunar Reconnaissance Orbiter also bouncing signals with Arecibo off the moon, and this NASA mission actually collected those signals to learn about the moon's surface. And Arecibo did a lot of really awesome education outreach. There were programs for college students, high school students, teachers, and a visitor center that thousands of students and families per year, both in Puerto Rico and visitors from outside of Puerto Rico, could go and visit, and it was incredible. And now we get to the present. So August 2020, the first cable broke. November 2020, the second cable broke. So we didn't know, we thought it was stable after the first one, and there were repair plans being made, but unfortunately it wasn't as stable as was thought. And so the second cable broke, and at that point it was sort of just probably just a matter of time. So December 1st, 2020, the remaining cables broke, the platform fell and destroyed the dish. There are videos. I'm not putting it here so that you guys don't have to watch me cry, but you can find the videos online pretty easily if you didn't see them already. The reaction was pretty heartbreaking. So as Michelle said, it was really sad to see. Here's just a few examples of different Twitter things that got really popular, what Arecibo means to me, stories that were written by scientists, by students, by users of the telescope, by retired folks that just cared about the telescope. So many people that just wanted to express how important this telescope was for them, either for their career or just because it was inspirational. So it was a really sad day, of course. But now we're looking to the future. So what's next? There are still parts of the observatory that are still operating. So that's important to know. There's smaller telescopes. There's a LiDAR facility. There's a remote sensing facility being built on a small island off the coast of Puerto Rico that was supposed to kind of work in unison, but can work on its own as well. So there's still a lot of operations happening. And there is so much data to analyze. So we have, all these years of operations of data, to still dive through. So there's a lot there as well. But that said, we're not happy with that. I hope you guys aren't happy with just that. So not only did the community come together, but the team at the Arecibo Observatory worked extremely, extremely hard in the wake of this otherwise very tragic event to put together a concept for a new telescope that we're calling the Next Generation Arecibo Telescope. It's a very different design than the current one, with the idea that let's take what we learned from Arecibo, let's take the advantages still that are held at that facility, at that location. So the fact that we already have a bunch of infrastructure in place. Being in that karst topography mountainous area means that there's reduced radio frequency interference. But let's do something bigger. Let's do something better. Let's look at all those small faults with Arecibo and do that better. Let's get more powerful radar. Let's get more sky coverage. So the fact that the dish couldn't move, the platform could. So you got a little bit of extra sky coverage, but the dish itself couldn't. So maybe let's get a big radio dish that we can actually move around a little bit. And get more sky coverage. And honestly, the support from the Puerto Rican government and the people to continue its legacy is huge. And so that's really an important factor. And so I know I'm talking so long. My final thoughts, the Arecibo Observatory was the most powerful radar system and one of the largest and most sensitive radio telescopes in the world until the day it collapsed. This was an old telescope, but it wasn't an obsolete telescope by any stretch. It was still on the forefront of groundbreaking science. The observatory and its team endured hurricanes, earthquakes, and so much more throughout the decades that it was operating. So my true belief is that the Arecibo Observatory will come back, and it will come back stronger. Thank you.
Thank you. It's an amazing talk. I know as I was hearing some of the news of people wanting to rebuild Arecibo, the theme from the Bionic Man was coming into my mind. We can rebuild it. We have the technology. I was like, yes.
If you want to read about the proposed telescope design and the science that we want to get, there are some links right here. And I sent Michelle the links to put in the chats as well, so you guys can access them. And you can actually have the opportunity to endorse it yourselves. So we're going to show this document to the National Science Foundation and to Congress and to other places that we can hopefully convince people to help us rebuild. So you can endorse it and have your own say in helping us get it rebuilt.
Awesome. Yes, please do check out these links, folks. This is a major legacy that we want to keep going for the next generation of scientists to explore the universe. All right, so now let's take some questions for Tracy. Question number one, if you were to write the next AO message, what would it look like?
Oh man, put me on the spot with that, huh? I don't know. People that think about this way harder and are more clever than I am on that front, I think, have done it. We did a message on the Voyager spacecraft as well, and I think the initial contact does have to be kind of like, what are we? And where are we in the universe, so that they can respond to us. And I'm pretty sure that's already what's covered. So I don't know if that's exciting. Maybe we can send some cat photos or something. That's pretty. I feel like that's very Earth unifying, is to have a cat decoded into there somehow.
I don't know. They might think of like we're like Egyptians or something and we worship cats.
I mean, on Twitter and Instagram, I think that's true. So I think it's okay.
Fair. All right. Next question. All of those asteroids in Earth space was fascinating. What surprised you about some of that research?
Yeah, so one of the things that's cool to think about is that, as kind of scary as those plots can look, we've never accidentally hit an asteroid on our way out of the solar system, right? With any of our spacecraft. So while there are a lot of them, they're really, really, really far spaced. It's not as densely packed as those kinds of plots can look. So I think that's always been surprising. You see pictures or movies of the asteroid belt, and it's all these things that you have to avoid, and even the asteroid belt, which is way more dense than the near Earth space of asteroids. You're not really dodging asteroids when you're going through it. So I think that's always something that's hard to imagine, because you see these plots and you see these movies, and then you just have to remember that all these things are really far apart. But in general, just a lot of asteroids are really interesting. I'll echo Stephanie's talks earlier about Psyche. There's just asteroids some are metallic, some are rocky, some are a mix, some have differentiated like planets have. So there's a lot of really cool stuff about asteroids in general. But the near Earth ones, I think what interests me the most is just the fact that we can nail down their orbit so precisely with radar. And I'll say Arecibo was the most powerful radar. We do have one other sort of operating radar facility in the US right now, which is at Goldstone in California. And that does, that does the job as well. It's just not as powerful. So you can't necessarily reach as far as you could with Arecibo.
All right, next question. How is this type of telescope aligned with objects to be studied, considering it can't be steered, quote unquote, and RF is slower than light waves?
Okay, so really good question. So the radio waves are light, so they're traveling at the speed of light. And you're right. So we can't point this big giant dish, right? That's stationary. So that's why they came up with this platform concept. So this 900-ton platform that hangs above the telescope, or hung above the telescope. That dome that you see, it's hard to. Can you see my mouse or no?
Yes.
Oh, okay, great. So this dome can actually slide up and down along this. You can see this beam thing here. So that actually slides, so you get this angle, which gets you a little bit more sky space. And then this arm that it's hanging on can do a 360. So you can actually, well, they say like 720. I don't know. It spun around in a circle, so you could get a lot of extra coverage that way. So that was a pretty awesome and ingenious design, in my opinion. That got upgraded to the telescope after. It wasn't the original design, but not long after they built it, they realized, hey, we could do some really cool radar science. So that's when they put it in.
Awesome. Yeah, we kind of can see it right behind your head. So
yeah, you can go up and down that thing.
got it. Next question. What is the frequency range of the observatory?
That's a good question. So the radar itself worked at 230 2380 megahertz. So that was sort of the wavelength. It's what we call the S-band radar. And some of the other facilities do slightly shorter wavelength, like C-band. But yeah, we were operating at 2380. But some of the other, the parts that were looking at the ionosphere, there was like a 430 megahertz. So those were the frequencies that we were using for those techniques.
Awesome. Next question. What led to the failing of the first cable, and what can be done to prevent the next generation telescope from that happening?
Yeah, so the next gen, at least in its current form, and it very much could evolve to end up looking exactly like the original, but better. But the current one doesn't have any of these major hanging parts. So it won't necessarily happen with the next one. We are not still 100% clear what happened. The first cable basically pulled out of its locked position at the top of the tower. You can see that it's in this, you can see that these wires kind of connect up to these towers. And it kind of just pulled out, and we're not really sure why or how that happened. I will say that Puerto Rico did experience some crazy seismic activity earlier in 2020 as 2020 went, right? Just January, the whole telescope was shut down because there was just nonstop earthquakes happening in the area. Did that contribute? I don't know. The hurricane in 2017, Maria, which was really devastating for the island of Puerto Rico and other places, may have had some effect as well. Although, of course, all of these things were checked out after that had happened too. So it's not fully clear. The second cable snapped was a surprise. So these cables were rated to hold the amount of weight even with one failed cable. So we thought it was only at 60% its max holding capability. And yet that one legit snapped in the middle somewhere. So, maybe just wear and tear over all these years. The cables weren't really as strong as we thought. So maybe some combination of nature and human issues or manufacturing issues. It's not 100% clear to us yet. They're doing the studies though, for sure. And I would say that if we were to rebuild, again, this thing was built in the 60s, right? So a lot of this technology, a lot of the materials were really, really old, and things improve a lot in 60 years, 70 years.
All right. Next question. What was the furthest object observed by Arecibo?
Ooh, that's a great question. So with the regular telescope itself, we're looking at like galaxies with crazy redshifts, meaning that they are like early beginning of the universe, galaxies that formed billions of years ago and are really, really, really like some of the farthest things away that anyone's ever seen. With the
like
radio.
13 billion light years away.
Yeah. So, I don't know if we went quite that far, but really far into the early days of the earlier part of the universe. With the radar, the reach, I'm pretty sure Saturn's rings was probably the farthest we did, or that they did. When I say we, I mean all the scientists there that were there for decades and decades. I've never seen anything further, and I think Saturn was kind of the reach. Keep in mind, you also have to worry about, you send the radio signal out, you have to be able to catch it with that dish as well, right? So the Earth is spinning in the meantime. So if you send out a signal to go too much farther than that, you'll have already rotated away from where the signal would bounce back to. So there's also that limitation, as well as just the power of the radar itself. So Titan's also at Saturn, so Titan and the rings probably.
All right, are there any other questions? These are very good questions. Are there any more? All right, if there are no more questions, thank you so much again, Tracy, for an amazing talk. I know I was excited to hear what the next step is for Arecibo, and here's hoping for the future. In fact, cheers to Arecibo with hopes that a brighter and better future.
Thank you so much. Thanks for having me.
All right, with that, thank you all for coming. Have a wonderful evening, and we'll see you next month. And have a great evening.